All right, so I think we'll get started. We're very happy to have Bruno Klingler today talking about special loci for complex local systems.
Thanks a lot, Jacob. So it's a pleasure to be here, and thanks for the invitation to speak. All right, so I will give a very elementary talk. I apologize in advance for experts. Let me first start with some kind of intro for the motivation of the thing. So the general theme is the relation between the geometry of smooth and maybe projective, in some cases, varieties, or C, and the finite group. So in this talk, I would be only interested in algebraic varieties whose finite group is infinite. Okay, so you can ask two very general questions on which we know very little, which is, first of all, characterize such pi ones inside finitely presented groups. Well, this question has been asked by Sarah. It's completely open. We know a lot of restrictions. For instance, we know that Sn and Z is not finite group of some smooth projective variety. Another question that you can ask is the following. So you fix x, and with pi 1 of x infinite. And then you would like to understand the algebraic subgroups of pi 1 of x. And by this, I mean guys which are of the form f flower star pi 1 of y for y to x, and maybe you ask that y is normal. And this is also completely open. Even for example, let's take AG. Okay, so pi 1 of x, of course, with some called blah blah. Pi 1 of x is sp2gz. And then you can ask what are the subgroups of sp2gz, which are images of some algebraic varieties mapping to AG, and nothing to say about that. They are very general. So, and it seems extremely hard just because of the discrete nature of the group. So the idea is let's try to linearize a bit all this. And basically, the moral of the story is that whatever we do with pi 1 of finite groups of smooth algebraic varieties, basically we know only how to look at their finite dimensional linear representations. Not exactly true, but to some extent, it's an accurate picture. Okay, so let's linearize. This means that rather than considering pi 1 of x, I will fix a local system with complex coefficient on x. And associated to this, I get an algebraic group, which is the algebraic monodromy group. By definition, this local system is given by some representation of pi 1 of x equal to GLV. And I can take the image of the representation. So this is a finitely generated subgroup of GLV. I take the Zariski closure of this image, and I take the connected standard definition. So this is an algebraic subgroup of GLV. And of course, I will assume that this group is positive dimensional. In other words, V is not torsion. Okay. So, what are these local, special loci I would be interested in? Well, the first remark is that each time I have y inside x, then I can associate to it hy, which is a monodromy of the local system restricted to y, or maybe actually to the normalization. It's better to work only with normal varieties when you talk about finite group. So you have an heteromorphism from the normalization of y to x, you pull back the local system, you take the algebraic monodromy group there, and you want to understand that. Okay, so the basic definition is why a small monodromy for V if well, HY is a strict subgroup of HX. Okay. And more precisely, you can also say that Y is a monodromy special for V if it is monodromy small. Monodromy small and maximal among the Z's such that HZ is equal to HY.
But you should fix a base point. So, I mean,
Yeah, okay, so everything is up to conjugation. I don't want to enter into the discussion of this.
Why do you have solved why? I mean, we could do all maps to X.
Sorry?
We could replace y in X by y to X.
Yes, but
So do that already. with-
sure, I could do that, but you would see in some sense, I don't think it will not, I mean, depends only on the image and the normalization. So, okay, so the monodromy special loci that I want to consider, the big monodromy locus for XV, well, this is the union of all the the y's with small monodromy, or equivalently, this is the union of all y monodromy special for V. Of those y's. Okay.
Shouldn't this
So-
be a small monodromy look? Sorry, but I just want
Sorry.
why is it the big monodromy?
I will come to that in one second. Yeah, okay. No, it's a big referred to monodromy locus. It's not big monodromy.
Oh, okay.
So, okay.
No,
That's
I
a good
understand,
point.
I understand. The big monodromy.
Big of monodromy locus. Because I'm taking all this, and inside this big monodromy locus, I will have a smaller one, which I will call the monodromy locus.
Makes sense.
So just a remark, you ask yourself the following question. Basically, if you take an algebraic variety X and you take a random Y by an algebraic procedure, let's take a complete intersection of ample stuff, then the image of the pi1 will be finite index in pi1 of X. And so it will, this Y will never have small monodromy for any local system. Okay. So basically, we really want to detect those subgroups which are really much smaller. All right, so let's look at some example, and what was discussed mainly this week is as the simplest case, which is a case where V underlies the VHS. Violation of Hodge structure. And there we understand everything, a lot of things. So there is a fact zero that I should emphasize is that because this complex local system underlies the local system, all the groups that I'm considering are defined over Q. So it puts a lot of countability into the picture. Are defined over Q. This is fact zero. Inject some countability. Fact one is that, of course, for ZVHS, it's in some sense a much more geometric object than a general local system because you have a period map and you can analyze everything using the period map. So out of V, you get the period map from the identification of X to some period domain associated to the monodromy group of X. Okay. And well, in general, and are defined on Q, and not only this, there is a crucial fact proven by Delin that those guys are semi-simple. So no unipotent, but no tori either. Really simple. So yeah, so HX, well, to isogeny, it's a product of simple factors. And so this means that this period domain is actually a product of such period domains for us. Now, let's suppose you have here. Suppose let's write this period map. If you have a y which has small monodromy in it, then this means that the period map will factorize to through a period domain associated to its own monodromy. And so you see that everything is controlled by the geometry of those period subdomains inside the period domain. Okay. So what do you get out of this? Well, you get a number of things. The first thing that you get is that this big monodromy locus for my VHS. So this will be the first is that this is a countable union of irreducible families of monodromy special subvarieties. Right, because the monodromy special, they will be exactly the pre-image of some such domain, and then depending of the nature of the group of Y, you would get families because you have a product structure there. So let me be more precise. Actually, if you analyze better, what you get is that you get a finite union. Yeah.
Monodromy locus. You should demand that the monodromy of HY is non-zero. Otherwise,
No.
You're not.
Wait a second.
Full points.
Wait a second. So, it's a finite union of irreducible families. So, the description that I gave as pre-image was the most interesting case, which will be the monodromy locus, and then there is a trivial one, which is the one you are talking about. So, it's a finite union of irreducible families of HY monodromy special. So guys which are monodromy special with monodromy group HY, monodromy special, where HY is normal in X, in HX, is contained in a normal subgroup of HX. Strict normal subgroup of HX. Union, a countable union of HY monodromy special, so no families, where this time HY is not contained in any strict normal subgroup. Next. So let me explain. So the typical example, you suppose HY is trivial, okay? Then basically what you are looking at, you are just looking at the fibers of the period map. Okay? So this gives you a family, or finitely many families decomposing, if you want to decompose into topological types.
Not completely, because you have you look at the connected component of
Yes. So it corresponds exactly to the guys where the image is a finite. So algebraic monodromy is trivial. But you can generalize a bit this picture by projecting two factors of HX, and this will also give you such families. So the moral is that you have to keep out of this picture is that as soon as HY is contained in a normal subgroup, then you can analyze through some kind of Shafarevich map by projecting to the quotient and taking the fibers. They will always have been monodromy special, and with this. And the other ones, actually, they are kind of isolated. You cannot move them, the maximum ones.
Can I?
Sure.
So monodromy special, here is HY, and you define it how, the monodromy special?
I define it as being the algebraic monodromy for the normalization of Y.
So you say that it's a countable union of what? Because we start with X, right?
Yeah, I start with X.
Uh-huh.
I look at those monodromy special subvarieties and their union.
But
And I'm saying that,
special subvarieties for HY.
no, for
For
HX,
HX.
Sure.
Yeah. And then you say
so it's a
for HY.
finite union of irreducible families of some monodromy special, which have the property that their monodromy group is contained in a
But
strict
then
normal
it's
subgroup.
HX monodromy special, not HY monodromy special.
No, but okay, so
This is by
when I say
definition.
HY monodromy special here, I mean it's monodromy special for V with algebraic monodromy group
Okay,
HY.
okay. It was just a.
Yeah,
okay.
just a matter of
Yeah.
elimination, sorry. if it was
Okay.
not clear. Yeah,
I think I just missed the assumption. Are you assuming X is projective or are you using
No.
like representation to get the algebraicity of these?
well, yeah, sure. I mean, here, when I say that, actually, you have to understand that the fibers, you don't really need. It's clear from Hodge theory that the fibers are algebraic. What is not clear is that the image is algebraic. But for the fibers, it's just Hodge loci for the product of pentadiagonal. So
But why isn't the big monodromy locus equal to X?
it can be.
Told you.
In this finite union, it can cover X. This is why I will discard this thing and only study this one. This is exactly the point.
I told
You
you.
see, do something stupid. Suppose you take X and you replace X by X cross P1. Then, of course, the P1 has trivial fundamental group. So,
I think Greg is complaining that technically all your points have small monodromy, so if you union them.
oh, yeah, sorry, here, yeah. You're perfectly correct. Here, I take Y positive dimensional, sorry.
You need to take Y with positive, with non-zero monodromy, I think.
No. I can take Y, it gives me some fibers, and those fibers can cover it. But I discard them in my definition.
Ah, okay.
It's perfect. Okay? So here the Y are positive dimensional. The Y is so Y, dim Y. I should put dim Y everywhere. Take the positive. More questions about that? So you see, your objection about the ones with trivial monodromies are in this family.
Oh.
And what I'm saying is that actually you get more. The right assumption is about, yeah, sorry for getting the dim Y strictly positive.
And don't use color.
Hmm?
Don't use red like that.
Sorry?
Don't use the color. Don't use. Don't
The
use
red
the-
is very tricky.
You don't like the red?
Well, it's because.
Trying to read.
Yeah.
But I just wrote A and B, just because I will need them later. I will not write anything more. I mean, there will be a C, but. Okay, so what I wanted to say is that, yes, so this part here, as I said, you analyze through fibration. So why is that a finite union? Well, because HX was semi-simple. If I take, essentially I can reduce myself to projection to the various here in gamma I. These are the guys defining the maximal normal subgroup there. Okay, so this gives me the finiteness. And as I said, here, those guys are the form, you take fibers, family of fibers. And you project to D8X, or H, where H is this normal subgroup. And yeah, this is really what you're doing. Okay, good. And those ones, on the other hand, with this condition, which will be as a crucial one, you want the monodromy to contain a strict normal subgroup. This is what I will call the monodromy locus of X3. Okay. And now, actually, this is the only thing that we analyze. But the miracle of Hodge theory is that this thing, by doing this result that the monodromy group is normal inside the Monforte group, is that this is actually the Hodge locus, which has a property that the projection on each factor is positive dimensional. That is positive. I call totally positive. This is the same thing, but in some sense, this is not really what I'm interested in here. I'm really interested in this guy. Okay. So now this is the true monodromy locus to some extent. A third fact, I'm already late, okay.
So here you need the catalytic link coupler.
Sorry?
Here you need catalytic.
Yeah, of course. Yeah. You start with the result that Ajax in normal, and then you have to use the catalytic. Actually, okay. All right. So now, what is a second fact? Fact 2 is that we can, using the PN map, we can continue the analysis of this. Can analyze using intersection theory. Well, exactly because of this diagram. My monodromy special, I can interpret them as being the pre-image of the intersection of this thing with the image of X in this period domain. And so out of this, I get the notion of atypicality, which was one of the main topics of the week.
Is that true that if something lies in the smaller period domain, I mean for Y,
Yes.
and comes from X, then it comes from Y? Is that you were just
So the monodromy special are really exactly the irreducible component of the pre-image of this.
it's not okay, fine. I don't see.
I take Y, I take its monodromy group.
Mm.
If it is monodromy small with this monodromy group, its image will be contained here. And so this means that this guy will be contained in monodromy special, which is exactly the pre-image. Of course, there is something non-trivial, is that this pre-image is algebraic, but this is what we got from a definability of the map or transfer. Okay, using intersection theory. So the definition is that in this setting, you can define a notion of being rare, which is, suppose I'm monodromy special. And then I will say it is atypical, which is a notion we use the entire week, if it does not have the expected dimension, but the larger dimension. So if the codimension of phi of yn in phi of xn is strictly smaller than the codimension in dhx of gamma x of dhy gamma y in dhx equal gamma hx, right? This is a standard notion. And so out of this, you get that the monodromy locus, so the small one now, because I want to concentrate on this one, is the union of the atypical one, where you keep only the atypical components, and the typical one. Okay. And so this is the last time I use the red thing. The small c is that we have the following theorem. This Greg. This theorem has been generalized by Baldi and overlaid to variation of mixed structure, but I will not talk about this today. Is that this monodromy locus? So now, a priori, this is a countable union of such guys, but actually, this is finite union of maximum one, so it is algebraic. So, okay, that's nice. This is not exactly what I want. I really want to study MLXV, but the next theorem is that generically, if the variation has level high enough, then actually the full monodromy locus is atypical. And this is the one. By 1. So all this is pretty strong. You analyze the big monodromy locus, you exhibit the part you are actually interested in, which is a mysterious one. All the rest is analyzed through fibrations. And then you get that actually, in most cases, this guy is just algebraic. So just reminding the classical case. So now what I want to do is to get out of the setting of the images. So let's move to the case I will be talking about today, which is the most important for me, which means that I'm assuming that Hx, of course, is positive dimensional and reductive. So general semi-simple local system. But now the monodromy is only reductive. So let's try to analyze this case in a super baby case.
Level being at least 3 means that is at least.
So the level being 3 means you look at the Hodge structure on the Lie algebra and you ask that the depth of the Hodge filtration is at least 3.
I'm saying there's 4 non-zero Hodge numbers.
No, 3.
3 numbers. So it's like H2 of a.
No, but it's not about odd numbers. It's on the adjoint.
Yeah, on the
On
edge.
the adjoint.
So like H, if it was H.
So you have the G00, G1 minus 1, G2 minus 2, and you want the G3 minus 3. I don't know if you were counting. You were counting.
That answers the question.
Okay, yes, with 1.
So typically for families of hypersurfaces of sufficient large degree, you are this. All right, so let's start with a baby case. Suppose that X is projective. So in some sense, you can skip the next 10 minutes. I will explain things, but this is not the way I finally think about those things because it becomes too technical and actually not so precise. So, but nevertheless, as a motivation, let's take a stupid example. I just assume that my local system is given by character, right? So this is really the trivial case. And let's be naive. So now what happens is that of a smooth projective varieties, you can understand local system either as being given by representation of fundamental group, or as an algebraic connection, or as a Higgs bundle with certain properties. So let's start thinking on the Betty side, right? So you just have a character of phi1 of x. So it will factorize through H1 of x, z. And you have a character going to C star. So this corresponds to your local system. Okay, so now you are really asking, when does it happen? Was that when I restrict to phi1 of y, I get essentially a finite group, is what I'm asking. So one way of thinking about this is that I just get an element in H1 of x C star. So I apologize for doing this stupid thing, but I think maybe. So for simplicity, suppose that, so here you have your local system, the class of your local system. For simplicity, suppose that it's really 0 here. So this means that I can understand it through an element here. And by Hodge theory, I can just take the non-zero part if I want. But in any case, what happens is that if I look at the big monodromy locus, what is it? Well, this is a set of y contained in X, such that, as I said, V tensor n becomes trivial for some n in restriction to y. And so this means that this is a set of y in X, such that alpha, this one form restricted restricted to y becomes rational. Okay. This does not look super engaging for trying to understand the structure of those things, right? Not super exciting. Okay, so of course, in this very simple case, there is a standard solution, which comes from the existence of Albanese varieties, right? Because after all, you can also say that you have a universal map from X to the Albanese, and actually the local system V comes from a local system here. And so in some sense, you read everything on abelian varieties. And so you see that the big monodromy locus of XZ is nothing else than the Y in X, such that V restrict Alban X becomes trivial on Alb Y.
So
Sorry.
you have to kill the substitution in H2.
Yeah, okay.
Yeah.
Let's kill them. Okay. And so this means that actually what you do, you just define an abelian variety associated to your local system, which is the largest abelian subvariety of Alb X on which this local system is trivial. And so this means that actually what you get a map from X to Alb X, Alb X mod this abelian subvariety, and then the big monodromy locus is exactly the union of the fibers. So again, we are back. This is very coherent with the first picture with ZVHS, because here the group is multiplicative. So the only interesting subgroup is the trivial one, which obviously is not there. So you have to get some kind of Shafari fibers. This is what you get here. So so we get a countable, you get even a finite family of subvarieties. All right, so now the problem is, suppose you get out of this, so your group is not the stupid multiplicative group, it's an honest GNC, for instance, then what can you do? You don't have this, it will never factor through the Albanese, so you have to do something. Okay, so let's try to move to the Higgs side. So, in general, better to look at Higgs. So, what you know is that if you look at your local system, this is exactly the same thing as giving yourself a holomorphic vector bundle with vanishing furniture class, which is non-abelian Hodge theory. Non-abelian Hodge correspondence, let's say. So you get an element in peak 0x, a line bundle, and you just get a theta holomorphic one form. If I'm back to this character, so corresponding to. Right, in this very trivial case. So the case is super trivial in the theory of Higgs bundles, and the reason is that those two notions are decoupled. Theta has nothing to do with E, okay, which is super special to rank one. And so now you understand what is the big monodromy locus. This is, I will not write it because I'm already late. It's the locus where this guy becomes trivial. So why this line bundle has to become trivial. And then moreover, theta has to become 0. Okay? And so actually you compute explicitly, in some sense more explicitly, what is this B. Let me not write the details, but at least you see that from that point of view, it's kind of maybe easier to consider these things. All right, so. All right, and if you continue in this line of thinking, let's see what you can actually prove, which is pretty easy, is that if X is smooth projective, then actually the big monodromy locus of XV is a countable union. You prove A. countable union of irreducible families of algebraic subvarieties. And what is the argument? Well, the argument is it's completely non-explicit. It's just you look at the Hilbert schemes of X. And so if you have a component T in the Hilbert scheme, then over T you have the universal family of varieties it parameterizes. And this is mapped to X. Okay. And now what you say is that your local system V, which now corresponds to a representation rho from pi1 of X to Hx, and Zariski-Dance with this guy being reductive, you think of it as being an X bundle. So it's P, a principal Hx X bundle. So, which means that this is a principal algebraic Hx bundle plus theta one form in omega 1 of at P. Which is a fiber bundle associated with the representation of Hx on its Lie algebra. Okay. And so now you understand that what you want to do, you want to consider the Y such that, first of all, P restricted to Y becomes trivial, admits a reduction to a smaller group. So admits a reduction to a group HY, which is strictly containing X. So let's fix the group H that you want. And this is the same thing as saying that over Y, you have a section of P modulo H. Okay. So really, you're looking at the locus where this bundle admits a section. This is the first thing. And second, you will do first this step, and then the second step you will do is you also want the theta factorized through the underlying P H, the bundle with structure group H. And this is a vanishing thing. You ask that the natural map from theta there vanishes to the associated quotient. So theta vanishes in some H1 X, or maybe I don't want to write everything at H1Y at P mod at H tensor omega 1. But the only thing I want to say is that those two conditions are completely standard algebraic conditions. And so arguing on the Hilbert scheme, you first construct this locus, and then you intersect with a second locus like this, and you get it. So it's a bit abstract, technical, heavy, whatever you want. It's the essential problem is that this is completely non-explicit. Okay. But at least you can get that. The second problem is that, of course, if you go to the quasi-projective case, then non-abelian Hodge theory exists, but it's much more heavy. You have to be super careful and so on. So I decided to stop there on this approach and just come back to actually the nice Betty world. So, okay, so back to Betty's side now. So first theorem is the following. So you can take X quasi-projective, you could also take it normal, it doesn't change anything. And you take a local system with algebraic monodromy group Hx, and Hx is reductive. Then the first part of the theorem is that you prove in general this. So you prove A, namely that the big monodromy locus of X is always countable union of irreducible families of algebraic varieties. Okay, so this is not that surprising, but at least it clarified my mind at that step. I was happy. And B is now I can play the same trick as before. Essentially, what I claim is that inside BML there is a nice mysterious guy MLXV, which is exactly the union of all monodromy special Y with an age Y not containing normal subgroup of age X, not contains in a strict normal subgroup of age X. Right, same as for CVHS. And then the claim is that this thing is the interesting part of the term is the point that this is a countable union of monodromy special subvarieties X. So, okay, fine. This is the same statement, but for free, and this is the thing that surprised me and which is interesting, which are strongly rigid in X. So I will explain what I mean by strongly rigid in 1 second. But in particular, those components they are defined, for instance, on the same algebraically closed field on which X is defined. So in particular, defined any algebraically closed field which is defined. So in particular, for instance, if you start with an X which is defined over Q bars, and those monodromy special in MLXV they are also actually defined over Q bar. So so let me make some comments about this. If you think about Shimura varieties, well, this is super well known, this is strongly rigid. I mean, it's well known that Shimura subvarieties of Shimura varieties, you cannot deform them at all. And basically what I'm saying is that it has nothing to do with the geometry of Shimura varieties. It's a more or less trivial fact. Everything I'm saying is completely trivial for that. And also, this is related to the question if the Hodge loci are defined over Q bar, if your variety is defined over Q bar. And what we prove with David and Anya is that this is true for exactly for those components. But actually, again, you don't need Hodge theory. So I'm just cutting the branch on which I was sitting for some time.
So is this the same positive dimensional Hodge loci or defined?
Sorry?
This says.
Yeah, of course. The main point is you are back to the original question is that for Hodge loci, the only remaining question is really understanding points. All right, so this is the theorem. And also I should mention, I'm not writing this today, is that if you want to understand the complementary locus, as I said, this is completely described by the theory of Shafari maps, which was well known in the case of projective varieties by the work of Esidio and so on, and which was developed by Ben, Johan, and Jacob recently in the quasi-projective case. So really an interesting guy is that one. Something.
Sorry, can you clarify that last comment? What are you saying about the complementary locus?
Well, the complementary locus, you want to analyze as a Y such that age Y is containing a normal subgroup of age X. So what you do is you look at the representation, you take the quotient by that monodromy, by this normal subgroup, and you analyze the fibers, and that's it. All right, so I just want to emphasize that in some sense, Hodge theory blinds you about what is important. For a long time, I thought that what was important was that the algebraic group was defined over Q, and this is what gives you a lot of countability and so on. But actually, it has nothing to do with it. All right, so let me try to explain the proof, which is super easy. Modulo something you have to be aware of, and I was not aware before starting this. So what is the proof? Well, first of all, I want to clarify what I mean by a family of algebraic subvarieties. So what is it? For me, this is a diagram like this. You have a base B, you have a family of varieties over it, And in general, has only countably many connected components. B is the union of BI, is joint union, and I can even assume that the BI are smooth. Okay. Second, what I'm asking is that P, from a topological point of view, is a topologically trivial, locally trivial fibration. Is locally topological fibration. And the fibers are irreducible and normative. And third, what I want is that the morphism U is essentially an immersion, but not really. Technically speaking, what you need is that if you look at the restriction to a fiber UB B of in your family, so this map is a normal cycle. So this means that this is birational and finite. So basically what I'm saying is that the fibers, you have to think that there is a normalization of some subvariety of X. And now I'm looking at how I can deform those normalizations inside X. So an important notion is, I would say that the family is weakly complete. If this family in some sense is kind of universal in the following sense, each time I have such another family, then actually there exists a big open set, Zariski open set dense in Y, such that in restriction to Y0, there exists a unique mapping from Y0 to B, such that the family on Y0 is pulled back from my weakly complete family, such that so weakly completeness means that in some sense, this family testifies for all possible irreducible families of subvarieties. Okay. So you have to think that if you have a weakly complete family, it really parameterizes all possible deformations of all possible subvarieties of X. And now, yeah, the theorem I was not aware when I started thinking about those things is.
In those definitions, you have no flat method solution.
Yeah, so, sure. Everywhere it is flat, but actually, as I said, I'm even asking that topologically it's a.
That's fine.
Yeah. You have to put flatness. Sorry, sure. So now the theorem that I discovered in some papers by Kola is that actually for any X normal variety, such a weakly, and not necessarily projective, this is an important point, such a weakly complete family exists. In other words, it's really possible to parameterize all those normalization of algebraic subvarieties in topologically locally trivial families. Okay, and out of this, how do you prove the theorem? So this is the only theorem. It's not mine. It's due to Kola. It's the only theorem in the talk. So how do you prove A? Well, suppose you have an irreducible subvariety Y in X, such that when you look at age of the normalization, it is not the full guy. Okay. Then I look at the following family. Okay. So by the fact that there exists a weakly complete family here, it means that there exists an index I in my collections of indices, and there exists a point B in UI, such that actually this normalization is just a fiber of the family UI at the point P. In other words, I have UI to X to B, and I have Y normal here over here. Yeah. All right, so now what I'm saying is that when I put back my local system on X to the full family, then on that fiber, the monodromy drops. But now this is a topologically locally trivial fibration. So the monodromy drops and is exactly the same as the one on that fiber on all other fibers. Okay, so so you get that it has smaller monodromy on each fiber of UI over BI. Okay, and this gives you the result. Just looking at each family and deciding if on the fibers the monodromy drops or not, and that's it. So this is completely stupid. Sorry for that. B is more interesting. So now you want to parameterize the true monodromy locus. And here you understand again what happens. So for B, now you notice a bit more. Not only you use the fact that all the fibers have the same frontal group, but you use the fact that the pi1 of the normalization in this diagram is normal in pi1 of UI, because this is a fibration topologically. So this implies that if you look at the monodromy group of HI, then it will be a normal subgroup in the monodromy of the image. When you take the Zariski closure, I mean, this image is constructible, just take the Zariski closure. So it will be normal there. So now if Y is in the small monodromy locus, then what do you know? Well, you know that this guy is not containing a strict normal subgroup. So first of all, you get that this guy has to be the full group. It's a bit different from the full group. This is the first thing, otherwise HY would be normal in HX. This is excluded. This is the first thing. And the second thing that you get for free, sorry, is that, well, this means that the monodromy drops here too. So, but then this means that U of UIs R is also contained in the monodromy locus. Not only in the big one, but in the small one, because otherwise it would be contained in a normal subgroup, and so the smaller group would also be. So now if you assume that Y is maximal among those ones, this exactly means that Y has to be equal to this thing. So maximal and monodromy special satisfy that Y is equal to U of U of bar. And so this means exactly that BI is a point. The maximal one have a deformation space which is trivial. And that's it, they are strongly rigid. Okay, so this is the proof. I can you see that this is a complete triviality. Okay, so now I see. So now, of course, now that you have this, you're pretty happy. So I insist, this is pretty nice. This means that those guys have to be rigid. Okay, so I will come back to that at the end. All right, so what about C? C was getting some kind of algebraicity of this locus. And of course, now you have the feeling that you really use PL domains because this is the way you define atypicality. Okay. So I don't have yet a good notion of atypicality for those things, but the trick, at least the partial trick for now, is now to make the local system vary. So consider and why does it make sense? Just think about it naively. You know that this guy is a countable union of rigid subvarieties. When you will move the local system, well, the only question is because those guys are rigid, do they stay with smaller monodromy or not? Okay. So, the way you do this is fix H, semi-simple or reductive if you want. It's not very important. So now I will work in the Durham setting. So I could look at the Zariski dense representation in H of pi 1 of x. This is the Betty modular space, and I know that this is by Hilbert. This is analytically equivalent to M Durham, the linear Hilbert of M Durham algebraic flat connections with monodromy H. Okay. So theorem 2 is that now I want to think of MLXV as a function of my representation of V. So MLXV is constant very generically on I fix, sorry, I should on M, and what is M? M is an irreducible component of this. No. Okay. So it's constant very generically, which means outside of a countable union of algebraic subvarieties of M Durham, this monodromy locus is constant. And the second thing is that another semi-continuous function, which means that on the countable families that are excluded of subvarieties of M Durham, this monodromy locus can only increase. So let's make a picture if you want.
Are you assuming you're staying in some locus where the monitor would be?
Yeah, this is what I said. I stay Zariski dense everywhere. So you have your reducible components M, whatever it is. Then I remove a countable family of algebraic subvarieties. I look at this function. I'm saying that there is a value generic of this, which is this countable union of rigid subvarieties. And when I approach those strata, then actually this thing becomes bigger. There are new things that become monodromy small.
For the time being, is it projective or quasi-projective?
Actually, quasi-projective is enough.
And you don't impose something.
Yeah, I should be okay. I should be maybe more precise, but let's keep it this way. Actually, this is just a spreading argument on that side, and I don't think you see anything at infinity actually. I'm just taking the standard identification with singular regular. And so the corollary that you get is that, of course, it's not the thing that I aim into, but this is what I get now. If M contains a VHS of level at mux 3, then the monodromy locus of X V, it's a very general thing, is algebraic. Well, is not Zariski dense. Not. So why is that so? Suppose that here in some stratum you have in one of those strata you have such a ZVHS of level at least 3. So when I take my very general point, I can find a path where I approach that point, and what I'm saying is that this function is constant inside this thing, so it stays the same. And then here it will become bigger. There are additional components that will appear. But by the theorem with Baldi and Ulmo, we know that this guy here, this monodromy locus for this ZVHS, it is algebraic, strict. So this means that this one has to be contained in the one of that one, and so it's not as given. Okay, so I will just say a few words about the proof without writing anything. Just
It says with monodromy H, but
oh yeah. So M is I'm not in the boundary of M. I'm really inside M.
fixed H.
So and M it's a component there where you are Zariski. You don't, of course, if you allow the root to drop, then you're in serious trouble. It's just a spreading argument. It's not. This is a spreading argument where, of course, use the fact that this component of the monodromy locus, they are rigid, and so they are defined on the same field of definition as X, algebraically closed field of definition. So, and as I said, the corollary is just applying that with Greg and Emmanuel. Okay, so actually, I don't want to write a conjecture because it's filmed. The conjecture is that this guy, MLXV, is always algebraic, except if you have a ZVHS of level 1 or 2. Maybe this is too bold, but why not? Okay, so let me finish just by making some remarks that I find very surprising. Because, the remark is not surprising, but the fact that the locus that we talk about is not at all very surprising to me. So what is the true special locus? Is the following thing, and this guy makes sense for X even with finite fundamental group, is just consider the union of all rigid subvarieties, all family rigid. I think I call them all very rigid. In other words, this is the U. With my description, this is the union in I such of all the I such that BI is a point of U I's are. Okay, so this thing that is given completely abstractly and in some sense for free by Collar. And what we proved is that the moral of this thing is that it contains the union of all V X H with Zariski bands with H reductive of the MLXV. In other words, all those monodromy special loci are contained in this locus. And what surprised me is that I started looking at the literature and absolutely nothing is known about that locus. I think this is super hard to actually describe, although this is a very natural question. To fix X, you ask what are all the rigid subvarieties of X? Are they dense or not? So of course, in Shimura varieties, they are dense, and so on and so forth. So the question is, of course, if you want to prove some finiteness here, what I'm dreaming of is maybe there is a crazy result telling you that for some X, actually, this thing is algebraic strict. It looks super difficult. I have absolutely no idea how to do that. Even for Shimura varieties, I don't know how to describe this locus.
But Bruno, sorry, what's the definition of rigid? Like, is it?
This is the one I said, that you have a normal subvariety inside X. You take the normalization and you look at all possible deformations.
I see. Okay, so
in the sense that I defined there. So this is really this one. The base has to be a point. Okay, as I said, even for AG, I don't know what this locus is. Some remark is that for some Shimura variety, it's well known that this locus contains more than Shimura subvarieties. Okay, I will stop here.
Okay, great. Any questions?
But I'm wondering how much of the Fourier special loci is controlled by CVHS? I guess
This is a good question. So I should have emphasized this. I mean, in all this business, in some sense, as was really clarified, I think, by Greg and David, all this business about atypical intersection is just a question about being able to have nice parametrization of the monodromy special ones, the maximal ones. What I'm saying here is just that you have a countable family a priori, but what happens for CVHS is for ZVHS is that you're able to put all of them in a to over-parameterize them, putting all of them in a single family. So you know what they should be because you know that they should be the pre-image of some dy, at least at the level of the universal cover. For CVHS, already this, I don't know what to do. And the point is that if you think of a CVHS, if the monodromy drops, then at the complex place, of course, the monodromy has to drop. But at all the p-adic, of course, this is defined of a finitely generate field. You will have finitely many p-adic places to consider, but there also the monodromy drops, which means geometrically that the corresponding harmonic maps will have to lie in a sub-building of the lattice building of the big group. And so you see that you have to be in the pre-image of not only of this thing, but of the sub-buildings. And this, I just don't know how to even prove that this is algebraic. The pre-image has no reason to be algebraic there. So you are contained there, but it's not even clear this is an algebraic variety, so I cannot say that the maximal ones are those ones. And this is the main problem. So I don't know how to do it for CVHS. And in some sense, it's probably right that if you understand really CVHS, then the general situation should be, well, okay, we can discuss this.
Can you say something about this construction of this universal family of normalization by Collard?
Okay, so yeah, this is the main point. Again, this is an argument of Hilbert scheme, but you have to be much stronger than me in classical algebraic geometry to get rid of to pass from quasi-projective to projective. And so it's Collard would say, like at the beginning of any of his books, that this is a super standard Hilbert scheme theory. And this is really what he's doing. But again, the construction is it's completely abstract using universal property, but you don't understand anything of what you're doing. I think he has this kind of statement at the beginning of the proof. The proof is completely unenlightening, as any proof using a Hilbert scheme in some sense.
He's really using the algebraic fundamental equation.
No. He's using the topology. This is in his book on automorphic forms. And he's really using the topological form too.
That's precisely the reason why I'm asking, because it's not exactly the same problem.
Yeah, it's not exactly the same problem, but in his book, he's really. But I'm also using everything
I
is
thought you
topological.
were using the algebraic fundamental equation.
No,
I mean, the risky closure and from it, the zero
no, but in the statement that I gave, there is nothing about fundamental groups. It's just existence of a weakly complete deformation space. That's all. I'm not talking about anything else.
Yeah, just a follow-up. So sometimes for this rigidity, you don't have to think about the Hilbert schemes, you have to think about the Chow varieties. I mean,
Yeah, okay.
maybe these are
I did not check.
I
If you prefer the Chow variety, probably maybe you can make the argument with that. Again, Collard thinks that the two are essentially equivalent for him.
and I'm thinking about, if it can be computed, so Hilbert scheme is extremely complicated. Chow variety.
I didn't check if you can make his argument work using only Chow variety. I'm not completely sure. Actually.
Okay.
So I'm worried how to express that something is topologically constant. That's not a priori.
Yeah, this is also what I was surprised about, but he manages. You really stratify. I mean. Yeah, but you have to be very careful.
Yeah, because it's more than one dimension.
Yeah.
So
Yeah.
logically constant, I think. That is not so many issues.
It's not trivial.
No, but it's as you said, it's a stratification.
Yeah, stratification argument. You have to be a bit careful again.
I have a question actually about your result for level 3 Hodge structures, integral Hodge structures. In this context, could you make it work for, maybe this was related to Daniel's question and I wasn't exactly following, but for CVHS, could you make it similar?
So that's exactly the point. I'm expecting exactly the same result, except I cannot prove it.
But you can't use like I don't know, one of these like jet space arguments that Mach
No.
does so well.
I don't think so. And the reason is that you see, a priori, maybe I can just write something, is that
You don't have a demod gamma?
Yeah, you have, okay, so for the CVJS, you just have at the level of the universal cover. So
Yeah.
you have this thing, okay?
Yeah.
Now suppose you have a Y where the monodromy becomes smaller. So you have a Y tilde here. And so you know that it will lie in dy. This is easy to prove.
Yes.
But what you don't know is that actually Y tilde is, or the image of Y tilde and X tilde is obtained as a pre-image of dy.
Mhm.
And a priori, it has no reason to be true.
Mhm.
Because what you can do is you can replace this equivalent map by a map from X to, well, you will have dx, then you have finitely many practice buildings. Well, maybe other complex embeddings.
Okay, okay.
Okay, and then you see that each place gives you a constraint. Not only you have to be in the preimage of dy, but in the preimage of the subvarieties building. And this thing, you don't even know it is algebraic.
Other questions?
So,
One more and then we'll. Mhm.
so what's the candidate for atypical section?
Well, first of all,
Can you repeat the question?
what is a candidate for the atypical guys? So the claim is that for a generic local system, which is not a CVHS, everybody should be atypical. And this, in some sense, I think I can formalize. Why? For CVHS, as I said, this is tricky. Because as long as I cannot prove that the maximal atypical are really the pre-image of those pre-image of something like this. And inside here, you take a sub-Piet domain and you take sub-varieties building and you take the pre-image and you prove this is algebraic, then I don't have any candidate. And this is the main obstruction, really. If we knew how to construct them, then the same machinery would prove on the nose that actually this is algebraic.
Okay, if we have more questions, then we can find Bruno afterwards. Why don't we thank Bruno again for